Okay. Shall we start? I think, are you able to hear me, brothers? The chat box, please.
Yes, doctor.
Okay. Uh, I will start now, but I was thinking one more thing. Uh, because you're looking at the lecture remotely. So I think during the COVID, I had few recorded lectures so for this course. So especially for the online ones, I'll try to share the recorded ones. Okay. So hopefully that will be more helpful to you all. Okay. So let us start this chapter. This chapter is called, we are continuing the same clustering. And last time we finished something called k-means clustering. So I hope you remember a little bit about k-mean clustering. K-mean clustering is about grouping the data, right? And you randomly start with, let's say if k is given to you. I think one of your speakers are on, which is I'm hearing my own voice back. Please, can you please turn off your mics unless you want to ask a question? Okay. So k-means, we started off by talking about k-means. And in k-means, we basically said that there are some data points and we wanted to group them. So the way algorithm works is that if k is given, let's say, very quickly, if I can uh, draw something here so that it will help you remind. Are you able to see the screen with data points as well?
Yes.
Yes.
Yeah. So what I'm just drawing lines, not points, because sometimes people say that they are unable to see the points. So I'm just drawing a little bit short line instead of points. Okay. So imagine for this data set, if k is given to you, let's say k is given to you to be 2. What we used to do before, and I'm going to use another color for that, the algorithm used to randomly pick any 2 points, right? Any 2 points in the space. And then what it used to do was to find distances from both points, all points from this point, right? For example, first this one, and then with this one, the second point. And then it used to assign each this red point to one of those blue points, whichever is closer. And that's how you used to initially form the cluster, right? Initially form an initial cluster. Now, then in the second cycle, you used to take average, and then you used to improve, and then the cycle goes on. I hope you remember what we did in k-mean clustering. Any questions so far? Do you remember k-mean clustering, all of you? You can use your chat box, please, if you just want to say yes or no.
You mean the last lecture?
Yeah, the last lecture. Do you remember the last lecture k-means?
Can you make a recap, Victor? Just a recap, a quick one.
Yeah, this is what I was trying to do. So we were just doing that. You start with a random point and then two random centers. For example, in this case, two random centers. And then in each iteration, you used to take average, 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 and eventually the center would move and it will reach its true center. So that's how k-means used to work. Okay. So now we will see another variant of that, and this is called k-means is not the only one. There's another one which is used, and this is called k-medoids. Okay. And k-medoids have different names. In 1987, people used to call it PAM, partition around medoids. And then some people used to call it Clara, different versions of it. But the idea is somewhat close to k-means, but of course, there are some differences. Now, the first question you should be asking, why we need k-medoids when we have k-means and everybody is using k-means. So I'm going to describe k-medoids, and I'm going to then explain why people tried to come up with k-medoids when k-means was already there. K-means actually was there before k-medoids. And then there are some differences between what is called PAM, which is the old name of k-medoids, with another version of it, which is called Clara. Okay. So one of the things that when people start to work with k-means was that it was highly sensitive to outliers, meaning what? Meaning that when if we have a point uh, that is that is far away, for example here. So what will happen is that because each point must belong to a cluster, it will go like this, and the center will be affected by that, just by that one point. It will start to push towards that because of its very large values, right? So
How it will be affected?
you can see because this center is the average of all values, right? If you have one very, very large value, for example, I'll ask you one thing. So if I say 5 plus 2 plus 100, what is the average of that? Can you take the average? Or
Divide
maybe
by
let's add one more thing. 1. What is the average for that? Can somebody try to find me the average for that?
24. No, not 24. I mean,
So it is what? 100 plus 2 plus 5 plus 1, right? Divided with 4. So it's around 27. Do you think
mhm.
27 is representative of all the points? Just look at first 3 points, which are the majority of the point. Do you think 27 is really representing this? Does it look
No,
like, one of these? You were asking me the question, so I'm asking you a question back a question. So do you think that this 27 and others as well, do you think this 27 is representing these majority of the points?
what do you mean representing this majority?
For example, the first point is 152, right?
Mhm.
Does this average look anything close to that?
No, it's far away.
Why it is far away? You tell me why it
Large,
is far away.
large.
Because of only one extreme value. Because there was only one extreme value, right? So this one extreme value
Mhm.
affected the average so much that it got away from all other points. So this is one of the problems with k-means, that it is sensitive to outliers. It is affected by some very large values. So and its center becomes less representative since an object with an extremely large value may distort the shape of the cluster. So that is why k means has this problem. So unless you if you wanted to really use k means, one of the approach is to remove outliers first and then do k means.
Doctor,
Otherwise,
what does
yes sir.
distort mean?
Say again. Distort.
Distort.
Distort means, look,
Mm.
original, the first 3 points were like this, right? And the shape was like this. Because there was one very large value here, one large value here. The shape becomes changed because of this thing. Do you see that it changed because of this thing?
Mhm.
So distortion is about changing the shape. So this is called distortion. Okay. Okay. So what is the solution? So the solution is to use another technique called k-medoids. So k-medoids was actually a technique to make sure that when you're using data that has large outliers, which may affect your results. So instead of k-means, they came up with another approach called k-medoids. Okay, so k-medoid looks very similar to k-means, except that it is better at dealing with outliers. So instead of taking the mean value of objects in a cluster as reference points, so instead of mean points as reference point, medoids are used. I'm sure it is not clear to you, but I will make it clear inshallah very soon. But just remember, in k-means we were taking averages. to find the cluster center. Do you remember, all of you remember this thing, that we used to take average to find the center of the cluster? Or let
Yes.
me just remind you again. So if for example, if a cluster has these 3 points, so we'll take average of x, 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 y, 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 and then we can find maybe center somewhere here, right? Right. So this is what you used to have, in k-means. In k-medoids, you cannot have a point, a center which is not a point, meaning that you have to say you will not allow any of the new points to become center. You are not going to create anything like that. But what you will say is, you have to pick only one of the already existing points to be saying that this is like the most representative point, or I would say that this is like the most representative point. So I cannot create a new one as a center. So it has to be only among the existing points. So whatever existing data points are there, only one of these can become center. So you cannot create new centers. It has to be only an existing point that can become a center. What is the advantage of that? You'll try to pick a point in the middle of the data which is most representative. So that is basically the advantage of that. So k-medoids, which is also called PAM, partitioning around medoids, use existing points, not new points, as cluster centers. So this is one big difference. And the representative object are called medoids. So an example for you to give. So in your class, if you look at height, weight, so I will not say that your average height is 5'8" and your average class weight is 75 kilograms. No, I will not be able to see that. That was in k-means. But now I have to pick one person. Muhammad is the most representative person in terms of height and weight. So it has to be Muhammad or Hassan or Saeed, one of the ones who are like, which can be like a true representation of everyone else. So it's like, it has to be one of the points, and that point is called, medoid. So it has to be an existing one. You'll see examples and it will become more clear to you. Okay. So don't worry, even if you still are unable to get that. So uh, PAM basically starts with exactly in the same way as k-means. You start with an initial medoids. For example, k equals to 2. So just like k-means, you pick 2 points randomly. But this time you will not take average, but you will replace one point with another point in the data set, only within the data set, and see if you are able to improve. If you're able to improve, that's good. If not, then you try again. Okay, so you basically have to randomly try out different points. Again, with example, it will become more clear here. So Clara and Clara Ennis are just, I'm going to talk about them at the end. Because k-medoids, people discovered that it has some problems. Okay, so what those problems are, I will talk about them, and inshallah, you will be able to understand Clara and Clara Ennis. So leave these two for now till the end of the lecture. So let us look at the algorithm. Okay. Uh, Again, we have data set like this one, right? Do you remember we had data points like these data points that you're looking at, right? So what we do, we randomly pick any 2 points to start off with, just like in k-means. Okay, so this is what it is saying. Let me just go back. So arbitrarily choose k points as initial medoids. Okay. And then how do you use to assign other points to this center? Anybody remember about that? Who can tell me how you used to assign point? We used to first calculate something, and based on that something we used to assign. Who can tell me, what we used to do? None of you have reviewed anything? Anyone? Nobody remembers anything. I'm helping you
Doctor,
out, right?
Doctor,
Yes.
uh, you mean the X and Y and we take the Euclidean?
Yeah. So if you remember, we used to take Euclidean distance of all the points to the center first. So we used to find distances. Do you remember that now?
Yes.
And then based on this distance, whichever point is closer to whichever center you used to assign to that. So you're doing exactly the same. So you pick random centers and then assign each remaining objects to the nearest center based on exactly the same, the distances, the Euclidean distance or the Manhattan distance. Okay. So this will create your initial clusters. So you will say that, okay, these points are close to is cluster one and these points
Uh,
are cluster two. Yes.
Doctor,
Yes.
so so what you mean is the process it is 99% close or similar to the previous what we did.
Yeah, it's very close to what we did before with small changes.
Okay, what these changes?
I'm going to now go to the change, okay? So
Mhm.
once you used to assign points, okay, to for example, you used to assign these points to this cluster center, which you randomly picked, and you used to assign the rest of the points, for example, to the other one, to this center, right? Then you used to take average x, average y, so that you find a new center. Then it used to tell, okay, the average is somewhere else. So you used to take new center. That was in k-means. But in this time, you are not going to be taking new centers, but you will randomly select another point in your data set. So I'm not going to take average this time. For example, this average, I'm going to now remove this one. And I'm just going to say that I already tried these 2 points. I tried this point and that point. Now I'm going to randomly try another point, maybe this one, to see if this point will give me better results, or maybe this point, see if it gives me better result. So I can only try only amongst the points that are already available in my data set. I cannot pick anything outside. That's that is basically the change. So it says that how do you change the point that you would like to try out? Well, you're going to pick them randomly. So you randomly pick the rest of the points. And then you will see, is it like any use to switch center from this one to this one? Is there any use? Will it improve the cluster? If it does improve, then you make the change. Otherwise, you will not change. Okay. And then you keep trying, you keep trying, you keep trying. How long do you try? You keep trying until there are two possibilities. Until you try out all the points, or you have tried very long and there is no change, even though you haven't tried everything. Now, why do we have to do that? Because it is randomly you're picking up different points, right? So you do not know which next point, maybe the next point would be better. So let's just look at an example which will help you make it understand better. I'm still sure that you are still not been able to fully understand it. So let us look at this example and then ask me if you still don't understand, okay? Because I'm pretty sure that you are still unable to understand fully. So this is your data point. This is your data set. Are you able to see your data set here? So how many points are there in our data set? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points. Are you all able to see this data set? Okay.
Yeah,
Yeah. So for this data set, just like before, we are assuming that we are taking k to be 2. So what we did, we completely randomly pick these 2 points, just like in k-means. Okay, so these 2 points are randomly picked. It does not mean that these are like the point that have to pick every time. It could be any 2 points from your data set. Is that clear so far, so good?
Mm-hmm.
So you pick these 2 points, and then what? And then you measure Euclidean distance, Euclidean distance, Euclidean distance, Euclidean distance, right? Just like in k-means. So you start measuring Euclidean distances from every point to the first center, right? And then every point, then you would do exactly the same way, which is every point to the second center, right? Every point to the second center. Then what do you use to do? You used to compare. I'm going to first draw it, and then I'm going to remove all of those, because I'm sure you are unable to see it fully. So let me this will help you refresh. So for example, if this is the point, okay, its distance with this centroid is this much, okay, and its distance with the other center is this much. So you will assign it to point number 1, or you will assign this to point number 2.
Number 1.
Number 1, which means that you are going to say that this point is now in cluster 1. Okay, so exactly in the same way, based on the distance, you are going to assign points to cluster 1, and then you are going to assign, based on smaller distances, points to cluster 2. I think you can agree that just by looking at it, I'm doing the assignments correctly. Do you all agree with that? Can you see that based on smaller distances?
Yes.
Okay, so which means that this becomes my first cluster, right? And this becomes
And Doctor.
my second cluster, right? So this, you can see my clusters here: cluster number 1, cluster number 2. Okay,
Mm-hmm.
is that good enough? Do you understand up to this point, everyone? Please chat box, please. If you're not, I should not go forward, because then you will not be able to understand. Okay, Hamad says he's okay. Yes,
Doctor.
yes, Saeed.
The first cluster, the third point that is far away from the point that randomly selected. Why we did not choose the cluster 2, not the cluster 1?
Maybe we're just saying that this distance is small, just a little smaller than this one. Okay,
Because
if you measure this distance
with
is a little smaller than this one. That is why. Okay.
because with my eyes I
Yeah,
see it.
we have drawn something. So maybe we haven't done the accurate calculation. Maybe it can be, in the other cluster, but that's not the point. Okay. The point is,
Mhm.
each point goes to one of them. Okay. So
Okay.
what is next? The next thing is that now, because you have tried out these two centers, now you will not take average, because previously you used to take average, and average used to come like somewhere in the center, right? Somewhere in the center. So then you used to try those as new centers. But here, what you would try here is that now, because these 2 points are already midoids, and we call them midoids. So all the other points, we randomly pick one point. Here you can see that this point is now randomly picked. Now we would like to see whether, if we pick this point randomly, okay, is there any benefit to switching this as a center or not with this one? Or maybe this with this one, from your eyes you can tell that there's no use here.
Doctor, can
Yes.
you repeat, please? Can
Yeah. So what I'm saying here is that I'm going to just remove everything again. Okay, so what I'm saying here is that we already have these 2 points as, sorry, it is my pen. Okay, I'm already saying that we currently have these two as centers, midoids, right?
Mm-hmm.
Now the algorithm says that try another point as a center, any one of them, any of the one that are currently not picked as the center, any one of them, okay? It could be this point, it could be this point, any point, right? So imagine if we randomly picked this point to try, okay? So
Mm-hmm.
we would like to see if can we replace this point with this point as a center, or this point maybe even with this point as a center. So we would like to see whether switching these points will improve the situation. So you should ask me, what do we mean by improving the situation? Okay. So I'm going to explain it now. But basically, it has to do with closeness. So I want you to now pay attention to this one. Do you think this point seems like a good representative of this cluster, of this particular cluster? It has to be
Uh,
somewhere in the middle. The representative ones are more in the center of the data. Do you think it looks like, more representative?
what do you mean? I did not understand.
Do you see these points? This
Y-
cluster, I'm talking about this cluster.
yes.
Do you think this point looks like an average, a representation, an average value of all the points? Does it look like this?
It is close to the center.
But is there any point better than that?
Yeah, the right one.
It means that they can be a better representative. So if I randomly pick this point, I may actually decide to change my center from to here because it is more representative. So again, you can see that because it's more in the center, isn't it?
Mm-hmm.
So how do we define better representation? How do we define that it is more into the center? So we use something called a total error in the system. Total error in the system, which is called E. And this is a complex equation. So let me just go forward. Okay. I'm going to describe few things and then I'm going to come back here. I'll try to avoid the math part here. Okay. So PR, first of all, let's talk about P. What is the P? The data points you have in your data set. Is that clear? You understand what P is?
Yeah, the point that we randomly pick.
No, 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 not the randomly picked point. All the data points in my data, these are all P equals to 1, 2, 3, 4, 5, 6, 7, 9. All these points are P.
Okay.
Okay. And then OJ is the representative object of cluster CJ, which means that, let me just go back here. So if this is my cluster, cluster number one, this is my cluster number one. Okay. This is O1. Why? Because cluster one, C1, its representative point right now is O1. Okay, do you understand now?
You
Now
mean
C2 is the second cluster and its representative point, which is this one, the dark one. What should I call it? I'm going to call it O2. O2 is the
uh,
representative point. Okay.
so the representative point, the dark one, uh, we which we make it the center of each cluster is the O. The
O1.
C.
That's exactly correct. We'll be calling
Mm,
it the O's. So I
okay.
hope you understand this now. O, P, if you understand these three things, okay, then I'm going to explain something called the error. Error is nothing but distance between 2 points. So for example,
Doctor.
this is an O1, O1 distance with first point, O1 distance with second point, O1 distance with third point. So this distance is called the E, the error. Everybody understand what E is?
Yes,
The
Doctor.
error.
What is the S?
I'm going to come to it, but do you understand what errors are?
Yeah, the distance between the O and the other points in
Now,
the
not
same.
only that, but you sum all errors up. So all the errors, sum of all the absolute errors. So this is called E, meaning that I'm going to add this error plus this error plus this error plus plus this error plus this error, so all the errors I'm going to sum
So,
them up, and this will become what you
Doctor,
call the E.
Doctor,
Everybody understand what E is? Saeed, you
uh,
understand what E is?
yeah, but can you go back?
Let me clean the screen up, because I think or let me use another this one. Okay.
No, no, I have a question. No, no, I
Sure, sure, sure.
understand, but so you will add all of the errors, but the O1 with the point with the same cluster, and the O2 with the same cluster, and uh, the submission of each cluster, we will add them together.
This is how you are going to add. Okay. So you're
Is my
going to take distances within the cluster only. Okay. Do you see this one? I'm not measuring this point with the other one. Okay. I'm doing it only within the cluster.
no,
Distances within the cluster only.
Doctor, the first cluster you will add you will sum all the errors. Are you
This
going
plus
to
this plus this, these three of them. I'm going to add, the
yeah,
three of
Doctor,
them.
yeah,
Yeah.
I know, but are you going to add the result of the cluster one with the result with cluster two, or no?
You didn't let me say this, because I never mentioned that. So I was about to then mention that I'm going to then add all the errors together.
Mhm.
Okay, so these errors plus these errors, so I'm going to add the total error in the system. Okay, so you will see an example, and you will be able to understand this better. So this is called error. Now, what is S? S is something called a cost function. So when I calculated all my errors of the original problem, I call this E old. But when I'm going to try a new point, you can see here now I'm trying a new point here.
Doctor,
This one. I'm
Doctor,
going to calculate all the errors again, and this one I'm going to call it E new. The new my new try, right? So I'm then going to take the difference between E new and E old. Now, errors. Do you want these errors, total errors, to be small or to be more?
small,
Small. Which means that what do you like? E new to be smaller or E old to be smaller?
old to be bigger, I think.
Yes, E new to be small, right? Because next time if E new becomes smaller, this is good. It means you are improving, right?
Mhm.
So
And Doctor,
if you get E new minus E old to be positive, or this difference to be positive or negative, what do you want this number to be?
positive?
Why positive? E new, you want E new to be small, right?
Yeah, but
Small number minus the bigger number. E new is small,
okay,
right?
yes, so it will be minus.
Minus is what you like. It means that if the number becomes negative, it means you found a better replacement. So you replace O random with the older one, with the O one of the whichever is closer. Okay, so one of the
Mhm,
OGs.
mhm.
Now let's look at an example, okay? And then you repeat the process. Basically, then you repeat the process. Let's look at this example, and then inshallah, you will be able to understand things better. Now you have these data points, okay? First point is uh, 2 comma 6. You can see here 2 comma 6. This is point 1. Can you see this point 1? This is point
Yes,
1, 2 comma 6. You
yes.
can see it's 2 comma 6, right? Which is shown here, 2 comma
Mhm.
6. And then you have 3 comma 4 and 3 comma 8, so you plot all of them. Now
Okay.
imagine O2 and O8 were randomly picked as the centers, which means that they O2
Uh,
and O8 are Actually,
Doctor,
we randomly selected as medoids, the
which
centers.
one? Which one? The center? Can,
Yeah, randomly selected to the red ones.
okay.
You know, just
Three
randomly
and
selected.
4 and 7 and 4.
Yeah, you can see 3, 4. It's 3, 4.
Okay, and 7, 4.
Yeah, 7, 4. So I have randomly selected this point. Okay, these 2 points. Imagine K2 given. So next was that you have to take distances and then you assign to the nearest cluster, just like the Euclidean distance. As I mentioned, you can see here that these 3 points are close to 2, and the rest of the points, I think even I is telling you that they are close to
Doctor,
8, right? So which means that
uh,
when you take the Euclidean distance, so how do you take Euclidean distance, for example, between point 8 and point 5 here, for example, point 8 and point 5, this one. So if you
point.
remember what is point 5, this is
Ah,
my point 5, and this
so
which is my point 8, this is my point 8. So how do can you help me write Euclidean distance formula? So
uh,
it will be,
the square root of 7 minus 6 square plus 2 minus 4 does not affect the result.
yeah. So
1 square is 1 plus 2, 4, so it is 5.
square root of 5, right?
Mhm.
That's exactly your take distance, okay? So based on that, we created cluster 1 and cluster 2. So you can see that cluster 1 has point 1, 2, 3, 4. And cluster 2 has point,
Doctor,
yes?
after we take all of these, what will we do? For example, the first result, the square root of 5. After we finish the cluster 2 and the cluster 1, and we will end
Okay.
of
Okay,
O1.
let's do it completely. Okay, let's try the same distance with 2 and 5, okay? Because this is
Oh,
we are trying with between 2 and 8 and 2 and 5, okay?
why 2 and 5?
Because these are the two centers, right? So we have to try with this center, and whichever is closer, we have to assign it to that cluster.
Even the 6 with 2,
Sorry, I did not get your point.
0.6 with 2, with point 2 also.
No, no, with all points, basically all points, you
Yeah, yeah,
take
yeah.
distances and the closer one, just like K-means. It
Okay.
was the K-means thing.
Okay.
So once you have assigned that, now what you have to do is to now calculate the errors. How do you calculate errors? The errors are exactly what I told you. Okay. Sorry, just a second. Uh, you have to find distance between 1 and 2, and then 2 and 3, and then 2 with 4, right? And then 8 with 5, 8 with 6, 8 with 7, 8 with 9, 8 with 10. So do you see
Okay.
here distance between 1 and 2, 2 and 3, 2 and 4? So what is common here? Because we are talking about the first
Uh,
cluster errors. So this is like the errors coming from the first cluster, okay?
Doctor,
Absolute distance. So this is cluster 1 errors done, okay? And then what is the center for the second cluster? Others please participate as well. 8. So you will see here 8, 5 with 8, 6 with 8, 7 with 8, 9 with 8, and 10 with 8. So you take distances. And
uh,
imagine these were the distances found by Manhattan distance, for example, or Euclidean distance.
Doctor,
Yeah, just a second, let me complete. So this is distances, errors from cluster 1. These are the errors from cluster number 2. Okay. So 3 plus 4 plus 4 plus 3 plus 1 plus 1 plus 2 plus 2. So the total distances turn out to be 20. Is that clear?
I have a question.
Yes.
Can you before we did before a Euclidean to take to and the result was the square root of 5. Where it is, I
It's
did not.
because we use Euclidean distance here. They are just giving you an example, and I think they were using Manhattan distance, which gives you different result. Okay. They were not using because they didn't show the calculation. So maybe I showed you with Euclidean. Maybe they were using Manhattan in this example. Okay, because distance itself is not important. So one of them is actually maybe one of these 5 with 8. This is what it is. So if you take
So
Euclidean, it is 1.14. But if you take Manhattan, maybe it turns out to be 2. Okay.
so both answer is correct.
They will be correct. I'm saying that this actual plus minus is not important. Whichever Euclidean or Manhattan, you just have to calculate the error based on whatever basis you're using. Okay.
Mm-hmm.
Okay. So let us just continue. So now we have the error. What was the next step? The next step is that we wanted to now try out another point. Now we randomly selected point number 7. Again, it's a random choice. It could have been any other point. Now, what you do is you again take these errors. Now, because we didn't touch the
You mean first?
the first cluster, so you will see that this didn't change. Okay,
Mm-hmm.
but because we changed a point in this cluster, so only the numbers change because now you're looking at distance between not 8 but 7 with 10, 7 with 9, 7 with 8, 7 with 6, and 7 with 5. So
Mm-hmm.
if you add all the errors up, what is the total error now?
22,
Before it was what?
20.
20. So what is our S here? You
Uh,
remember what was the formula for S? The new error
minus the
minus
old
the
one.
old error. So is this a negative number or a positive number that we got?
Positive.
So this is greater than 0. So shall
Yeah.
we switch 7 with 8 or not?
No, because we want a smaller, not a bigger.
Yeah, so because the cost, the error has increased, that is why we have decided not to make the switch. Now, what is next? What is the next step? The next step
Try,
is after
try
trying
another
7,
point.
we will try another point. Okay, for example, point number 10 or point number 3 or point number 1. And then we have to keep trying. We have to keep
Doctor,
trying. We have to keep
sh
trying
shall
until
yeah,
yes.
shall we change the point of cluster number 1?
It could be any if we randomly pick a point from point 134, so then we
No, no,
will.
what I mean, because we changed the cluster to the point, shall we
No, we
change?
look, Saeed, please understand this. We were trying to switch. We
Mhm.
only tried 7, but the
No, no,
number turned out to be greater than 0. The error increased, so we
yeah,
did not change.
I know, but what I mean is, uh, for example, can we change the cluster 1 point and the cluster 2 point and try again? Not this example change cluster 2 point. Can we make the change for both cluster and try?
You can, but normally in K-meteor, you try one at a time, 1 point at a time.
Ah, okay, understandable.
Okay, 1 point at a time. Now it could be from anywhere, but it has to be only 1 point at a time. Okay. But the thing is that if 7 would have given you better results, then you would say 8 no more, and you would have made 7 the new center, which means that you would again find distances and make new clusters and then try again, try again, try again. Now the problem is uh, We never made the change because the error was higher, right? Because the error turned out to be higher. But if this error would have been less, imagine if this number turned out to be 19, would you have made the change?
Yes, I will.
So which means that now seven and two becomes the new centroids, medoids, and then you take the distances and reassign the points. So that's how you keep going. But my question is, do you see a problem with this approach? Who can tell me what is the problem with this approach?
It takes much time.
No, tell me a logical approach. Time, fine. Someone else, please
Mm,
participate. What is the problem you're seeing with this thing? In K means every time we used to improve. If we are not improving, it basically meant that we have reached the optimal point. So what does happen with this thing?
mm. You cannot know are you going to improve or not.
Okay, others, any other view?
It may go in a bad way.
No, I mean you're just guessing, but there has to be a more logical answer. What about others? Muhammad, Hamad, Hassan, all the other people here in this class. Rashid, no views from anyone else? That's why I wanted to have it in class. Suleiman, Rayan, Marwan, Faris. Okay, you're basically the problem is you're running on your luck, which means that because you're trying points by randomly you're trying points, which means that every time you're trying your luck, isn't it? Do you understand that?
Yes,
Because you're hoping that by luck you get a good point. There's no systematic way of improving, isn't it? Every
yes.
time you try your luck, you try your luck, and you try your luck. Now imagine you're trying your luck and you have not 10 points here. Imagine you have 10,000 points. Then what will happen? What is the chance of getting a good cluster center in 10,000 points? Do you think chances will be small or high, or as the number of
Small,
points are increasing?
small.
Not just small, very small, because the number of points become large. The larger the number of points, the more your chances of getting good cluster center become smaller and smaller and smaller. Why? Because the chance of picking, let's say, 1 out of 10,000 points is is 1/10,000. Very small chance, right? So it means that the only other way is to try all points. If you start trying all 10,000 points or 100,000 points, your computer will take forever, right? Can you imagine that? Because you're trying everything. So again, not the best way. That is why people do, despite the fact that k-medoids will is not affected by outlier, people still don't use it because
So
it is very inefficient.
the K-Meadows is efficient with a smaller point.
If only it only works when you have small data sets. Okay.
Mm,
By the way, when you accept changing the point, all four possibilities can be there. For example, a point from cluster one may jump into here, a point one in cluster one may stay here, okay, or a point may jump from here to here, or a point
why?
may still stay within the cluster. So this is basically case one, case two, case three, and case four. Okay.
Uh,
So because you're
wh-
updating the clusters, and any one of them can occur. You can see here, for example, a point jumped from cluster number one to cluster number two here. So PAM is robust than k-means when it comes to noise, or especially to be more precise, when it comes to outliers, PAM or k-medoids is a very good technique. But the main disadvantage is that it only works when your data set is is very small. It doesn't work with the large data sets. Okay, it does not scale well with large data sets. Scale meaning that it becomes very slow when it comes when you're dealing with large data sets. Okay, so k-medoids is very costly. Okay, it's really costly. Much more costlier than k-means. K-means runs very fast. Okay, but in both k-means and k-medoids, you basically have to tell k before you do anything. Okay. So that's one thing. Now the thing is that if you still that does not solve the problem. Okay, that if you have outliers in your data and you don't want to use k-means, then what? Uh, then people try to develop what is called Clara. Clara is, we are not going to go it mathematically, we are not going to see, but I'm going to just show you conceptually what Clara is. Okay. But Clara
So,
works, it's just a modified version of PAM or k-medoids, the method that we just learned.
so what we learn just the logic.
And you're just going to see, what is the difference between Clara and k-medoids in a bit. But Clara stands for clustering large applications. Okay, so this is where the name comes from, Clara, clustering for large applications. So what they do here is that because you have very large number of data points. Okay, so what you do in Clara, you randomly pick a small sample. Because you're randomly picking small sample, so you expect points from every equally picked from all sides of the data. Okay, equally picked. But instead of now you having 10,000 or 100,000 data points, you have a small data set, 20, 30, 40, 50. Okay, it's a small data set. Now this data set, you're hoping that it is a representation of original population. Now, as you can imagine, the larger the sample, the more, the better, isn't it? Do you agree with that?
No.
I'm talking about the representation, not the efficiency. Sorry. Okay. Let's look at this data set. Okay. If I pick only pick 2 points, and I randomly pick this point and maybe this point, my chances of picking representative points is low or high when I pick such a small sample with only 2 points in it. Very small, right? But if I pick 10 points randomly, 1, 2, 3, 4, 5, 6, 7, 8, do you see that my chances of picking more evenly from every place? But if I pick not 10 but 20, I will, so my sample will become more and more representative. But you should not pick so large that it gets close to population. Okay, so you still have to pick a sample, but sample has to be large enough so that it represents your population.
Victor?
Yes.
I did not understand your point. Can you explain it with a simple way, in a simple way?
Yeah, I was just trying to explain through the same example. Let me try to explain again. Okay. I'm going to go one by one. Okay. You just have to randomly pick one point. Which point would you pick randomly? So I'm going to go close my eyes and click somewhere. Okay. So I clicked here. So is this a representation of the whole population? Maybe, maybe not. Okay.
Yes, maybe no.
So I said maybe 1 point is too less. So I'm going to randomly, again, I'm going to close my eyes, randomly pick. Oh, sorry, randomly pick. Maybe this point. Are these 2 point representative? I'm not sure, maybe not the best ones, right? So I'm going to go random, pick another one. Is this a good sample? Maybe it is improving because now it's covering more different parts of the data. Random, right? So maybe this one. Okay. Maybe try another one. So as I'm increasing the sample size, as you can see, as I'm increasing the sample size, I'm picking up points from different parts of my population because it's random, right? So equal
Yes.
chance. So by picking it up from more larger sample size, you get, you should be able to get more representative sample. But
Mm-hmm.
sample is still small. So if this is 10,000 points, okay, 10K points, and I'm picking 100 points as a sample, 100 points as a sample. Still 100 is a very small number as compared to 10,000, right? So
Mm-hmm.
I can run PAM on 100 points. I don't have to run it on 10,000 points, which will make my computers really, really slow down. Okay.
Okay.
So this is what Clara do. It runs on the sample, not on the actual point. But if you pick your sample good enough, then you'll hope that you get a good point. Okay.
Mm-hmm.
Now there's another version for this Clara, and this is called Clara NS. Okay. So what it does is, instead of picking one sample, just trusting one sample, it actually relies on, can you see what I just highlighted? It relies not
Yeah.
on one sample, but on multiple
Many
samples.
samples. Mm-hmm.
So you keep running sample one, then you keep running sample two, then you keep running sample three, sample four, many samples. Each sample is not big, maybe 100 points. But because you're picking for the first time, what 100 points you picked are maybe different than what the points you picked in the second time and the third time and the fourth time. And by picking those samples multiple times, you start to get, points which are actually very close to the two representatives. Okay. So
Mm-hmm.
this is basically what you call Clara, another version of Clara, which is called Clara NS. Okay. What are its
Mm-hmm.
strength? Its strength is that it deals with large data sets than PAM, much larger, not just large, very large data sets than PAM. Its weakness is that its efficiency depends on the sample size. And I already explained it to you. If you take a poor sample, the quality of results will be poor. If you take a good sample, representative sample, it will give you good results. Okay. So good results are based on samples, how good the samples are. Okay. Uh, Uh, okay, so sorry, just a second. So not necessarily that uh, so you basically there can be a chance of bias, especially if you're picking up sample bias, if you're picking up the samples not through a random process. Okay, so maybe you have a bias in on one side of the data points or something. So that may also cause problems. Okay. The main limitation is that if the best k-medoids are not selected among samples, Clara will never find the best cluster. So this is again another disadvantage. But it is like a trade-off. Okay, it is
Uh,
like
what do
a
you
trade.
what do you mean, doctor?
Okay, so if I go back here, uh, you remember in k-medoids, one of the points is the best. Imagine you're using K2. Okay, if I do
Okay.
if I do full 10,000 point clusters, okay, 10,000 clusters. So maybe these are the two clusters. Okay. Now
Mm-hmm.
imagine this is if I just try all the points. These are two are the best possible ones. Okay. Imagine I tried out all 10,000 points. Now when I'm picking up random sample, imagine I every time I pick this one, I pick this one, I pick this one, but never picked
Mm-hmm.
this one in my sample.
Mm-hmm. Mm-hmm.
If you don't pick that point if you by luck, if you don't pick this point in the sample, you will never be able to select the most ideal point. Okay.
Okay.
So this is another problem that you're improving your situation, but still there is a luck involved in it. Okay.
Mm-hmm.
You're trying to reduce the effect of luck, but still it does not mean that, there is no luck. There is some luck that you actually have to rely on. Okay.
Okay.
Now, we already talked about that. I'm going to stop here. Now, somebody asked me about uh, 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 the content of the exam. Are you able to get the exam date yet?